So what you want to do is you're going to take your test tubes and you're going to fill them with the water. Do this in a minute. Just listen for a minute. So I've got it where it's headed up. The opening is up, and I let all the air come out and I fill it. Then I dump the open end of the test tube. I turn it over while it's still underwater so it stays completely full of water. Does that make sense? And then you're going to stand the test tubes. That's the tricky part. And don't bang the table or it'll go. You want to stand the test tubes on the top. Yeah, that bouncing of the table, it will make them go. So you're going to have to sit back from the table for like 10 minutes, okay? Okay, so if this experiment works correctly, everybody see on page 83? Look on page 83. If it goes correctly, you notice in the picture that the test tubes in the picture, here's your battery, and here's your test tubes. One of them is half as full as the other one. That's what it's supposed to look like. It won't necessarily look that way, but it's supposed to look like that. And we're told here that the electricity is actually breaking down the water molecules. So why would we see twice as much in one side than the other? Yes?
Because there's twice as many hydrogen atoms as oxygen atoms.
Very good. There's 2 times as many hydrogen atoms as there are oxygen atoms, and so that's why we should see that when we break it apart. And if your experiment goes perfectly, then you will see that. But in most cases, it doesn't work out that way. Sometimes you see a lot more on one side than twice as much, and sometimes they look about the same. And it's explained to us on page 84 that that's what we call experimental error. That experimental error is when things don't always go perfectly when we're doing an experiment. Experimental error can be due to the people, or it can be due to the equipment, or it can be due to all sorts of different things. And it's important for scientists to be able to look at an experiment and try to figure out what's causing the experimental error. Now, with these experiments, it already mentioned that if your battery had a lot of gas in it, and that's why we let it sit for 10 minutes. Yeah, believe it or not, they can have oxygen and stuff locked up in them. And so if you don't let it sit for 10 minutes, that might throw the experiment off. But we did let them sit for 10 minutes, and we have in the past, and sometimes they still come out pretty weird. So what could be sources of experimental error on this experiment? Yes, Clay?
Using water fountain water.
There you go, getting cold water instead of warm water. We're about to see if that'll make a difference. It might, so we're about to see. I've never had anybody do that one before, so that'll be new. Yes?
Using old batteries.
Okay, using old batteries that might not have the charge they need to do it could affect it. If you used well water, it might have other minerals in it that react with the battery differently and therefore could mess up its process of breaking down the water molecules. Maybe somebody bumps your table and it falls over and there it goes, you know. So maybe when you put the water in your test tube, you didn't get all the gas out of it. And when you flipped it over, it started with some gas in it. So there's all sorts of different possibilities as to why you might have some differing results. And the example that we were given, we're told that scientists themselves, to try to keep problems like that from happening, they put themselves through a process called peer review. And personally, I've always understood that that's why scientists publish their work. Scientists publish their work for 2 reasons that I know of. For peer review, so that other scientists can look at their work and then they'll try to do the experiment over again and see if it's accurate, but also so that they can share their information so that other scientists can take that information and springboard and build on that information. And so that would be the peer review process. And that is very helpful. Now, usually, as it was mentioned in here, you want to get some peer review before you publish, which is a good idea, because if you publish and somebody else actually tries your experiment and it doesn't go well, then it can be very embarrassing. The example that he gave here was in 1989, doctors Martin Fleischmann and Stanley Pons told everybody they figured out how to do cold fusion. And cold fusion was the idea that you could make, basically, you could make energy for next to no money. And so that would mean all of our power would be almost free. You could take water molecules and stuff like that and do fusion and have an unending supply of energy. And we don't know how to do cold fusion. Hot fusion is the only kind we know how, and it's not efficient right now because you have to have temperatures like that of the sun to do it, and therefore it takes so much energy to do it, it's not feasible. But these two guys said they figured out how to do it cold fusion, and so the whole world was all jazzed about it. And then, unfortunately, when they finally submitted their experiments for peer review, nobody could reproduce their work. And so because nobody could reproduce their work, it's believed that they were looking at experimental error. They were not looking at the real thing that they thought they were. Now, there is actually a movie based upon this with Keanu Reeves in it called Chain Reaction. And it's a thriller, and I'm not suggesting you go see it, but it actually is a group of scientists that are supposed to have figured out how to do cold fusion and how all the bad guys want to stop them because they don't want a cheap form of energy going out to the world, you know, and so that's the whole thing. So this idea is one that a lot of people would like to see happen, but that's how the experimental error can come in, and the peer review can save you from a lot of embarrassment if you manage to get it when you need it. Does anybody see a difference in the size of their two?
Yeah.
Okay.
There's like no air in the right one.
And how much in the left one?
Quite a bit.
Yeah? Just let it go a little longer. Let's see what happens. Okay? So we're going to keep going. If your experiment went correctly, let's answer 4.1 because this can be really fun. Okay? So if you're not there yet, turn to page 85, please. And Cal, is there a reason your book's closed? Oh, because of the table. You don't want to shake the table, right? All right, well, why don't you share, Pete, do it carefully, Zach. Share with Zach for right now. 4.1 says, suppose you want a precise measurement of rainfall in your area. So you set a rain gauge outside. After it rains, you measure the level of water in the gauge and record the results. You then empty the rain gauge and wait for the next rain. There are at least two sources of possible experimental error with this procedure. One will lead to the measurement that is too low, and the other will lead to the measurement that is too high. What are these sources of error? So what'd you get for that? What's a source of error there? Yes, ma'am.
Well, it doesn't rain as long or as hard, like be exactly the same every time.
Well, that's true. So in other words, I wonder if that would play into what we're asking for here. Precise measurement of rainfall in your area. Okay. It might also rain at your house and not at my house 3 houses down, right? So that would possibly not give us the exact amount either, correct? Mm-hmm. Good. What's another one? The book gave us a couple, yes.
One that would definitely result in both kinds of misinformation would be a very oddly shaped container.
That could be. If you use an oddly shaped container, you might get strange results. What about if your cat or your dog came over and drank water out of it? Or even a squirrel. That could mess it up, huh?
Or you could put it under a tree or something.
Yeah, where more water hit it rather than less because it kept dripping off of the branches after the rain, right? And then the book actually suggested that if some of the water evaporated out of it because you didn't check it for a while, or if it didn't start completely dry and you already had some water in it, those were the two they came up with, but I think we could come up with a whole bunch more. Your little brother came by and tipped it out and then put it back, and, you know, I have a little brother, can you tell? Anyway, so does Wyatt. I can see the smile. All right, so when we want to express that water is made up of 2 hydrogens and 1 oxygen, we express it as H2O. And you guys have all been raised with the idea that water is H2O, right? That's not a big deal. But what we're looking at here is that hydrogen is represented by the H, and there are 2 hydrogen atoms attached to 1 oxygen atom. And there's a model in your book. There's a model in your book that looks something like that for the water molecule, which is the 2 hydrogens, which would be those 2 little white guys, and the 1 oxygen that they're attached to. And then this is a model, so these little legs would represent the shared pairs of electrons that these share, and that's what keeps the molecule together. Okay, but we would write this as H2O, and you don't write the 1 on the O because the invisible 1 works science as well as math. You know how if you have X, and there's only 1 X, you don't write the 1 there, but if there's 2 X, you write the 2 there? That's because the invisible 1 is working algebra, right? So really you don't see them, but there's a little invisible 1 right there, isn't there? There's also an invisible 1 under here, isn't there? There is. Well, the invisible 1 works in chemistry and physical science too. And so the invisible 1 is right here. And right here, and right here. Okay, we got a whole bunch of invisible 1s, but you don't write the subscripts on the ones that you only have 1 of. And so that's how you write a chemical formula. And the reason they came up with chemical formulas is because they used to have to write out water in the chemical way, you would have to write out dihydrogen monoxide. 2 hydrogens and 1 oxygen. This was very cumbersome at best. Can you imagine trying to write out a whole chemical equation and trying to use this? This would be a problem, wouldn't it? And so a guy in the 1830s by the name of Berzelius said, we have got to do better than this. And he said, let's make symbols for all of the known elements. And so they gave symbols to all of the elements that were made. And the reason some of the elements seem to have strange symbols is because they had Latin names. You have to remember that the sun never set on the British Empire in the 1800s, the 17 and 1800s. And so if you were a British scientist that discovered an element, you gave it an English name. If you were anybody else in the world, you gave it a Latin name. If you were Russian, if you were French, if you were German, you gave it a Latin name. And so they had either Latin or English names. And so when they came up with the symbols, they gave symbols for the existing names at the time. That's why, look at the very front cover of your book. You have a periodic chart in the very front cover of your book. See it? Do you know that was there? Well, now you do. And if you go along the left-hand side of that chart, the H stands for hydrogen. And because that was already used up, go all the way to the right on the top, you see HE. Well, that's helium. So you can either use 1 uppercase letter or an uppercase letter and 1 lowercase letter for the symbol. Go back to the far left again, and below the hydrogen, Li stands for lithium. But if you go right below that, Na stands for sodium. And I don't know about you, but I look at Na and I think, how did you get Na out of sodium? Well, because its Latin name is natrium. And that's where they got it from. Iron, which is Fe, was ferrous. And so they got it from its Latin name. So I just wanted you to understand, aren't you glad you speak English? At least most of them look right? That's helpful, isn't it? Yeah, can you imagine if you were Japanese or something? Or Russian? None of them would look right, huh? So we use their chemical symbol, and then we put a subscript at the bottom to distinguish how many of them there are. Okay, let's look at this one. I'm sorry I didn't have bigger ones of these to work with. Let's say that the yellow one is carbon, and carbon's symbol is a C. And let's say all these little brown ones, can everybody see it? All these little brown ones are hydrogens, and hydrogen is an H. What would be the chemical formula for this molecule?
H4C.
Okay, good. I already have this up here. It's actually CH4, but I would not count off for what you said. H4C, CH4. Very good. That would be the chemical formula. And there's a really good question there. How do you know which one to put first? Don't worry about it. Okay? In chemistry, you learn sometimes how to know which one goes first. It's usually whichever one has a positive charge after it goes through the process of getting together. But in CH4, neither of them actually develop a charge, so that's a good question. How do you know which goes first? And I think traditionally they just put the carbon first. because it attaches to all sorts of weird things. Life is based on carbon. God chose to do that. So carbon does all sorts of interesting stuff, kind of like water does all sorts of interesting stuff. So anyway, okay, let's see. So turn over to page 86, please. Oh, this is what we breathe. The oxygen. And it actually shares 2 pairs of electrons.
O2.
O2, that's right, very good. And this would be something more like, let's say this was hydrogen attached to, say, chlorine. That would be hydrochloric acid, HCl. And that's how you would write that symbol, because it's just one of each of them. So you would just write H and then C, capital C, little l, which is chlorine. And anyway, so that's how that works. This one kind of fell apart on me. This is, let's see if it's got 3. This is nitrogen. So what would the symbol for this molecule be? If it's nitrogen, which is an N, what would its symbol be? N4. Very good. Very good. Okay, so that's how that works. On page 86, we have some on your own questions. 4.2 says the chemical formula for baking soda is NaHCO3. How many atoms make up one molecule of baking soda? So first, count the atoms that make up that molecule and tell me how many atoms make it up.
4.
6.
2, 3. Okay, let me write it for you. NaHCO3. All right. 1, 2, 3, 4, 5, 6. Does everybody see that? Remember, if it has an uppercase and a lowercase letter, that's just one symbol. Okay? So 1, 2, 3, 4, 5, 6. Na is sodium, so you have 1 sodium, 1 hydrogen, 1 carbon, and 3 oxygens. That's what that would stand for. Okay, number 4.3. Vinegar's active ingredient is acetic acid, C2H4O2. How many of each atom are present in a molecule of acetic acid? So how many carbons are there?
2.
Good. How many hydrogens are there?
4.
How many oxygens are there? 2. Very good. 4.4. The sugar in green leafy vegetables is called glucose. A molecule of glucose contains 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. What is the chemical formula for glucose? So somebody tell me, what's the chemical formula for glucose? How many?
6.
Good. H what?
H12.
Good.
O6.
Very good. C6H12O6 would be glucose. And when you get to biology, you'll have to memorize that, because you'll have to memorize all sorts of weird things we do with glucose. Yes, Zach?
Ours is about like halfway now.
Oh, good. Okay, let's take a look at what we've got. The left-hand side has a whole lot, and the right-hand side has very, very little. And then in the next one, where is it? There it is. There's a whole lot missing in the left side and very little there in the right side. And then in this one, it helps when you have a bunch of them to do, because then you can really see the experimental error. This one barely either, very, very little gas on either of them, isn't it? It really is. And then this one, let's see if I can get it. It's got a whole bunch of gas on the left side, probably about 4 or 5 times as much on the left side than the right side. Now, let's look at that. Let's say we were using Carter and Ben and Clay's table. And theirs looks kind of like this. That would be H what O? What would you say? Maybe H5O would be representing that? Mm-hmm. Or how about the girls over here whose they didn't get a whole lot in either, did they? The girls have this. It looks about right? Okay. So let's say that was H. That might be H10O. Huh. That was really different. Okay? You girls, was there a lot of difference? A little bit. But yeah, yours was, I'm going to put your H on the correct side this time. Yours is kind of like that, right? So that might be, I don't know, H7O? Okay. I'm sorry? Okay, so we have a lot of experimental error going on there, don't we? You can go ahead, you don't have to worry about knocking them over anymore. If it gets knocked over, just don't worry about it. We'll clean it up after. Okay, let's see. Then we go on to water's polarity. Is the TV still right outside the door? Thanks.
Do you want it?
If it's still there, yeah.
It is.
Okay, just pull it in the room. We may use it. Thank you. Now that we're looking at water's polarity, and we are going to have some fun with this. That's the one thing with water, you can do all sorts of experiments. I need somebody like Zach with short hair. Do you put gel in your hair? Okay, can we use your electrons? Great. Yeah, back up. Actually, the more blown up it is, the better it works. Okay, now, hang on to that for a minute, Zach. And would you put those back in that baggie for me, please? Let's see, I need a regular pencil. Aha. Thank you very much. What I'm going to do is I'm going to make a regular pencil hole in the bottom of a styrofoam cup so that a stream of water, God willing, thank you very much, will come through the cup and go. Can everybody see? Okay. And let's see if we can get this to go straight down. Oh yeah, it looks like it's going straight down, doesn't it? Okay, good. Right, that's what we need. So the hole's correct. I'm going to get a little more water in here, and then we'll move this out of the way. Okay, now, this is the tricky part. What we're going to do, rubbing it on your head's the easy part. What we're going to do is you're going to rub it on your head, and then wherever you rub it on your head, I'm going to let the water run through like a straight line, and you're going to take the balloon after rubbing it on your head, and don't touch the water, but just bring the balloon over close to the water. What should happen is that the stream of water should jump towards the balloon if we do this correctly. Okay, and the more vigorously you rub your head, the more electrons you give it, the better charge, and hopefully the better it'll jump. Okay, so go ahead and rub your head for maybe 10 seconds or so. And then try not to block it so they can actually see it move, okay? So I'm going to go like this. Go ahead and just bring it towards it. Whoa! Did you see that? Wow. Here, turn this way and do it. Do it again. See if it'll do it again. Nope, you got to rub your head again. All right, hang on. That was great. Wow, you've got a very electric personality, Zach. Okay. Go ahead, rub it again. Now, do it this way so they can see this time, okay? Don't touch the water. See it bend? Oh, that's great. Do it over here so they can see. See it bend, guys? Can you see it bending? Girls, gentlemen, good job. Everybody give Zach a hand. Don't leave yet. We're not done. You're doing a great job. Now we're supposed to do this with oil, which is a real mess. Okay, so we're just gonna, so Zach, go ahead and rub your head. And then we're gonna do it with the oil, okay? Okay, go ahead and pull it, just put it towards the oil. Okay, it does nothing. Do you see it? Nothing's happening. That's perfect. You're done. Thank you. Everybody give him a hand. He's done. Yay, Zach. You can keep the balloon if you'd like. So, what did we see with that experiment? What we were supposed to see was exactly what we did see, because Zach has got a very electric personality, and I appreciate that. Zach was giving the balloon electrons, because when you rub the balloon on your hair, it gives the balloon electrons, which are negatively charged. So here's our balloon, and our balloon was negatively charged. Water molecules are slightly charged molecules. And because of that, the water molecules bent towards the balloon. Now there's a reason for this. Water is made up of H2O. Hydrogens are small and oxygen is big. Hydrogens have 1 proton and 1 electron. Oxygens have 8 protons and 8 electrons. They're much larger than hydrogen is. So what happens is they share, but because this guy is much bigger and he grabs the electrons more of the time, it's uneven sharing. And because it's uneven sharing, this guy has the electrons around him more often than these guys do, just because he's bigger and he can grab them and hold them longer. So this one, remember the electrons are negatively charged, so this one has a slightly negative charge on the oxygen side of the molecule, and there's a slight positive charge on the hydrogen end of the molecule. And it's literally because these guys can't hold on to the electrons as much of the time, so they're more positively charged. And you can think of this as these guys are more giving because they give it up, and these guys, give it to me. He's more of a negative personality, you know what I'm saying? And so that's the more negative side of the molecule. Now overall, the molecule is not a charged particle, but it's got a slight positive and a slight negative charge because of unequally shared electrons. Does everybody understand this? Because you will see test questions on this, and I don't want you to have a problem with it. So in the book, when it defines what a polar molecule is on page, is that 88? Get your glasses. On page 88, it actually says a polar molecule is a molecule that has a slight positive and negative charge due to an imbalance in the way the electrons are shared. So all you got to say is uneven sharing makes a slight charge over the molecule. Okay, that's what you need to say. And because, listen to the word polar. It sounds like it's got a north and a south pole, doesn't it? So there's a positive end and a negative end. Okay, because it's a polar molecule, uneven sharing, and so it does have a slight charge. Well, what happens then is the negative charge here attracts the positive charge. And so this molecule is frequently drawn like Mickey Mouse, okay? There's the oxygen and those are the hydrogens. And so if that's the case, it's the hydrogen end of the molecules that are attracted to the negative charges on the balloon. And that's why it jumped over towards the cup, which means if we were able to put a positive charge on the balloon, the water would have still bent towards the balloon. It just would have flipped around, and the oxygen side would have been towards it. Does that make sense to everybody? Because when it comes to electricity, opposite charges attract one another. Like charges repel, opposite charges attract, just like with magnets. You guys have played with magnets before, right? Okay, just making sure. So that's what a polar molecule is one with uneven sharing, and therefore there's a slight charge over the molecule. And we use the Greek small case letter delta to show that this is a slight charge, not a real charge. Other molecules have real charges, like table salt. Table salt, the sodium has lost an electron, so it takes on a positive charge, and a chlorine has grabbed its electron, so it takes on a negative charge, and those actually are ions. They are no longer atoms because they are charged particles, okay? But this is not the case here. It's a slight charge. It's not a complete charge, and therefore it gets the small case delta to show you that it's only a partial charge. Now, with the oil, did it jump? No, the oil is a nonpolar molecule, which means the oil doesn't have any charges over the molecule, and therefore there's nothing to attract it. It just goes down. It said that if you did manage to have some pops or something in it, it would happen if you had some water contamination in your oil, that the water in the oil might pop towards the balloon. I didn't see popping. Did you see popping? No, I didn't see popping either. But apparently that can happen at times. So, he reminds us that everything in creation has charges in it because everything is made up of protons, which are positively charged, and electrons, which are negatively charged. And so everything in creation has charges, but most of the things are equally balanced, and therefore you don't see things that are actively charged particles. But it makes it easier for particles to be dissolved, which we're going to talk about in the next reading that you do next week. Turn to page 90, please. 4.5. Suppose you had a positively charged object to hold next to the stream of water in experiment 4.2. Would the stream bend the same way as it did with the balloon, or would it bend the opposite way? We already talked about that, didn't we? It would bend the same way. The water molecules would just turn around. And then 4.6, hydrochloric acid, HCl, is a powerful acid often used in cleaning. While the H stands for hydrogen, Cl stands for chlorine. Chlorine atoms can pull on electrons much more strongly than can hydrogen atoms. And that was the one I showed you with the bigger ball and the smaller ball. Is hydrochloric polar? Is it polar? Would there be uneven sharing if one is much bigger than the other?
Yes.
Yes, thank you. 4.7, chlorine gas, Cl2, is a molecule composed of two chlorine atoms bonded together with a chemical bond. Is this molecule polar?
No.
No. Good, very good, thank you. And it's because they share equally. If they're the same size, same guy is going to be the same size, isn't it? They're going to share equally, aren't they? There's a little more to it than just the size, but for our purposes, we'll just work with the size, okay? There is a little more to it than that, but the size helps us. So we can just think of it that way for right now, okay? Now that's as far as you read, correct?